welcome to today's RSS Journal webinar, sponsored by Quintiles. We have today a main speaker, Peter Goos from KU Leuven, Belgium, who's going to talk about optimal design, getting more out of experiments with rapid change factors. My name is Stephen Gilmore. I'm chairing today's session. I'm Professor of Statistics at King's College London, and I'm also a member of the RSS Journal Webinar Advisory Group. And also, if I remember rightly, I was the editor of Journal of the Royal Statistical Society Series C when the paper that today's talk is based on was accepted and published in that journal. So that's just a nice coincidence. So that's enough for me, I think. It's time to introduce today's speaker, Peter Goos. He is Professor of Biostatistics in the Department or the Division of Mechatronics, Biostatistics and Sensors at KU Leuven, a nice city very near Brussels in Belgium. And Peter has many years' experience researching in design and analysis of experiments, especially algorithmic methods, which is the topic of tonight's topic, and also considerable experience working with engineers and scientists in industry on making these methods applicable. And the purpose of, generally the purpose of the RSS webinar sessions are to make the papers presented in the journal accessible to a wider audience and perhaps attract more attention for these papers where they can be useful. So without further ado, I'll hand over to Peter to give his presentation.
Thank you, Steve, for introducing me. Indeed, I will talk about optimal experimental design in the presence of hard-to-change factors. And the talk I will give today is based on a 2007 paper co-authored by Bradley Jones from the SAS Institute in the United States. And the title of the paper was A Candidate Set-Free Algorithm for Generating the Optimal Split Plot Designs. That paper was basically follow-up work on an earlier paper by myself and my supervisor, Martina van den Broek, which was published in Technometrics in 2003. And the Applied Statistics paper, the 2007 paper, inspired some more work in the same area. For example, Bradley Jones and I published a paper in Biometrica in 2009 on split plot designs instead of split plot designs. And there was also some more follow-up work published, for example, in Journal of Quality Technology. And today I will not just talk about the 2007 paper, but I will also regularly refer to the 2009 Biometrica paper. So I will discuss both split plot and split plot designs today. On slide number 3, you can find an outline for today's talk. I will start by some motivating examples. I will discuss the models typically used for data from split plot and split plot experiments, and I will discuss the most commonly used criteria for selecting experimental designs. And then finally, I will return to one of the examples to present an optimal design for it and to discuss some of its features. And I will conclude the talk by mentioning some recent work in the area of split plot and split plot experimental design. On slide number 5, I present the first example for today, and that's an example of an antibacterial surface treatment experiment. That experiment was done by a Belgian research institute to study the impact of 5 factors on the antibacterial properties of the lining of refrigerators. The 5 factors are listed in the middle of the slide, and a key feature of 2 of these factors is that they are hard to change. Now, what does that mean? Well, the first factor, the gap, and the second factor, the frequency, they require a technician to be changed. So to change the gap, to change the frequency, a technician has to be called, and this was cumbersome. While for the other factors, the power, the gas flow rate, and the atomizer pressure, no technician was needed. The experimenters themselves could change the levels of these factors without any trouble. So what the researchers in this study definitely did not like was a completely randomized experiment. They did not want to conduct all their tests in a random order so that they would have to change the gap and the frequency very often, because then they would have to bother the technician all the time. What the researchers did like is shown on slide number 6. On slide number 6, you can see a split plot design with 32 tests, 32 experimental runs, partitioned in 8 groups of size 4. And these 8 groups in the jargon are called whole plots. So we have whole plots of size 4 here, and the 4 individual tests within a whole plot are called subplots. Now, what you can see in the table is you can see levels for 5 factors. W and S are the gap and the frequency in the study, and T1, T2, and T3 are the 3 easy to change factors that I named on the previous slide. Now, a key feature of this experimental design is that the levels of W and S, the gap and the frequency, are held constant within every group, within every whole plot. So these factors, W and S, the gap and the frequency, are applied to the groups. They are applied to the whole plots of the experiment. Whereas the levels of T1, T2, and T3, they change all the time. They change essentially from run to run, from individual observation to individual observation, from subplot to subplot, and therefore we call the easy to change factors T1, T2, and T3 subplot factors. And W and S, they are whole plot factors instead. So that's the kind of experimental design that researchers like when they encounter hard to change factors. The next example on slide number 7 is completely different. That example does not literally contain hard to change factors. It does not literally involve hard to change factors. That example is about cheese making, and it's an example taken from a paper by Eric Schoen in the Journal of Applied Statistics back in 1999. Now, in that experiment, the goal was to produce cheeses in the end. But cheeses come originally from large tanks of milk, and the large tanks of milk are split into smaller vats where the milk is further processed, and in the end, individual cheeses are produced from the smaller vats. Now, in the cheese-making experiment published by Eric Schoen, 2 factors were applied to the large milk tanks, 5 factors were applied to the smaller vats, and 3 more factors were applied to individual cheeses. So we have 3 kinds of factors in this study. And in the jargon, this leads to a split plot experiment where the milk tanks themselves, the large milk tanks, are called whole plots. The smaller vats are called subplots, and the individual cheeses can be called subplots, as shown on slide number 8. And the factors applied to the large milk tanks, they are called whole plot factors, as I show on slide number 9. The factors applied to the smaller vats, to the subplots, are called subplot factors, and then the factors applied to the individual cheeses are called subplot factors. And in the modern literature on this kind of experiments, in industrial contexts, many people very often refer to the whole plot, the subplot, and the subplot factors as very hard to change factors, and easy to change factors. And that's also the terminology that certain softwares are using. So that was a second example. That was an example of a split plot experiment. And then I have a third example, and that third example actually inspired the 2007 paper. That example involves the use of polypropylene in cars, in the car production. And in the polypropylene experiment we discuss in the paper, 11 factors were studied at the same time. 7 of these factors were related to the way in which the polypropylene was produced, and 4 factors were related to the way in which the polypropylene was processed later on. These 4 other factors were related to a gas plasma treatment that was given to the polypropylene. Now, the overall goal of the polypropylene experiment was to improve the adhesive properties of polypropylene so that coatings, both water-based coatings and solvent-based coatings, would stick well to the polypropylene. The whole experiment was conducted in 2 stages, you could say. There was a first stage in which 20 batches of polypropylene were produced, and each batch had a slightly different formulation. And the 20 polypropylene formulations produced in that first stage were dictated by the levels of the first 7 factors in the experiment. And essentially each batch here was a large box with many little polypropylene plates that could be used for later experimentation. Then the 20 boxes of polypropylene plates were sent to another company, to another place in Belgium, where another company tested 100 gas plasma treatments on 100 different little plates selected from the 20 initial batches, the 20 initial boxes. So roughly speaking, about 5 gas plasma treatments were tested for each box, for each batch of polypropylene. So clearly we have a complicated experiment here, 11 factors, 100 different samples taken from 20 different boxes. On slide 12, I give some details about the way in which the 20 batches of polypropylene were made. The different formulations were defined by 7 two-level factors. You can read the names of the 7 two-level factors there. Now, one thing was special about the 7 two-level factors, and that was that talcum and mica, 2 additives, they could never be used together in the experiment. That was a specific desire of the researchers, and that was because in reality, in real life, when producing polypropylene for cars, they either use talcum or mica, but never the 2 of them together. So that was a sort of practical constraint on the levels of 2 of the 2-level factors. Another specific feature in stage 1 was that there was interest, of course, in the main effects of the 7 factors, but there was interest in very specific 2-factor interactions as well. Namely, there was interest in all 2-factor interactions involving EPDM. The researchers did not care very much about other 2-factor interactions. They thought these other interactions would not be important. So that's stage 1. On stage 2, on slide 13, we can see the details for stage 2. 4 factors were studied there, namely a categorical factor type of gas, and 3 quantitative factors, gas flow rate, power, and reaction time. A key feature of the categorical factor here is that it has 3 levels. There were 3 types of gas that were used in the experiment, 2 kinds of activation gas, and 1 etching gas. Now, regarding these factors, the researchers were interested in the main effects, all 2-factor interactions, and their quadratic effects, at least the quadratic effects for the quantitative factors. And on top of that, the researchers were very concerned about interactions between the polypropylene formulation and the gas plasma treatment, and therefore they really wanted to quantify interactions between the 7 stage 1 factors and the 4 stage 2 factors. As a result of all that, we have many factors which are nicely listed on slide number 14 together with their ranges. As a result of all these considerations, the model that the researchers were interested in is very complicated, was very complicated. And you can see the details about the model on slide number 15. If you count all the effects the researchers were interested in, there are 66 of them in total. And we have 100 observations available, so 100 is bigger than 66, so that should be doable. It should be doable to estimate all these effects. Now, by now it should be clear that this is not a traditional experiment and that classical experimental designs from textbooks cannot be used to set up this polypropylene experiment. First of all, as shown on slide 16, there is a multi-component constraint. Mica and talcum cannot be used together. There's a categorical factor at 3 levels. That's very unusual because textbooks on industrial design of experiments usually only talk about 2-level designs. And as by a miracle in textbooks, all categorical factors only have 2 levels. We have 20 batches in the polypropylene experiment. 20 is not a power of 2, so classical regular designs cannot be used. We have this specific interest in special 2-factor interactions. We have an overall sample size, which is also not a power of 2. And we're interested in quadratic effects for some quantitative factors and only in linear and interaction effects for some other quantitative factors. So it is clear here we need a flexible approach. Classical, nice orthogonal designs or central composite designs will not do the job here. Now, at the time of the polypropylene experiment, there was no nice user-friendly algorithm to set up this kind of experiment. So I had to work around that and I had to come up with an ad hoc approach for the design. Now, what I did was I set up an experiment separately for stage 1, and you can see that experiment for stage 1 on slide number 17. So I set up that design assuming that we were interested in main effects and in the 2-factor interactions involving EPDM, and I assumed we have 20 test combinations available. So that was my design for stage 1, created with proc optex and SAS back then. For stage 2, I used a very similar approach. I created the stage 2 design in an optimal fashion using proc optex, and the eventual design you can see on slide number 18. And one key feature of the design here is that if you look at the first column in that table, you can see 7 ones. So that means that the first box of polypropylene plates was used 7 times. You can see 6 2s below that. That means that the second box was used 6 times, and so on, and so on, and so on. In any case, the most important thing here is that not every polypropylene box, not every polypropylene batch was used equally often. So I ended up at the time with an unbalanced design. I had no other way to create a sensible design at the time. And of course, this design, this ad hoc design, is a useful benchmark for any algorithm for creating optimal split plot experimental design. So that concludes basically my introduction with examples of split plot and split plot experiments, and I focused, of course, a lot on the motivating example for the 2007 paper. Next part of the presentation is about the models that are typically used for data from split plot and split plot experiments in industry especially, and I will also discuss criteria for selecting experimental designs so that the models can be estimated properly. Now, in the models for data from split plot experiments and split plot experiments, we need to take into account the fact that the runs are grouped. In the first example I presented, the antibacterial surface treatment experiment, there's a grouping of the experimental tests due to the fact that we did not want to change the gap and the frequency all the time. In the cheese making experiment, there were two kinds of grouping. First of all, there were large groups of cheeses coming from the same large milk tank. And there was also a second kind of grouping, namely a grouping of individual cheeses coming from the same little vat. And then finally, in the polypropylene experiment, some experimental runs came from the same batch of polypropylene or from the same box of polypropylene plates. So there's also grouping in the polypropylene experiment. And that grouping has to be taken into account in the split plot, in the statistical model for the data. Now that was a specific feature of the models that Bradley Jones and I considered in 2007 in the split plot paper and in 2009 in the split plot paper. On slide 21 then, you can see some more details about the models that we used. We were very general in the models that we used in the sense that we could handle main effects, interaction effects, quadratic effects of quantitative experimental factors, but also of qualitative experimental factors. And the qualitative experimental factors, they could have more than two levels, as in the polypropylene example. And then in the model, we also needed random effects to capture the correlation between responses within the same group, responses collected within the same group. We needed to have random effects for the whole plots in a split plot design, and we needed to have random effects for the whole plots and the subplots in the split plot design. So for each kind of grouping, essentially, we have a random effect in the model, and with each kind of grouping, there is also an associated variance component. Now, one key feature of our approach, and basically all split plot models in the literature, is that we assume that the factor effects do not vary from group to group. We assumed that the main effects, the interaction effects, the quadratic effects are stable across whole plots and across subplots. So that was a key assumption. So essentially, our models were random intercept models. On slide 22, you can see some more mathematical detail. On that slide, you can see the models for individual observations in a split plot experiment and in a split plot experiment. The first equation you see is for the jth response within the ith whole plot of a split plot experiment. And the second model on the slide is for the kth response in the jth subplot of the ith whole plot of a split plot experiment. The key feature of the split plot model is that all observations in the ith whole plot have this gamma I in common. That gamma I describes that all observations, all responses in the ith whole plot are similar, And likewise, we have a gamma I in the split plot model to capture the similarity of all responses collected in the ith whole plot. And on top of that, we also have a delta ij, which describes that all observations in the jth whole plot of the ith, in the jth subplot of the ith whole plot, are also similar. Now we can also write that model in matrix notation, and that's done on slide number 23. That's the typical notation used for split plot and split plot models when you collect all the responses in a single response vector y. And in the split plot model, we have a gamma vector here, collecting all the random effects for all the whole plots. In the split plot model, we have the gamma vector again to collect all the random effects for all the whole plots in the experiment. And on top of that, we now have a delta vector to capture all the random effects of the second kind of grouping, the subplots in the split plot model. Now for all the random effects, we made the usual assumptions, and as a result of that, we got the variance-covariance matrices on slide number 24. On slide number 24, you can see these formulas describing which observations are correlated with what other observations. Essentially, what these matrices do is they make clear to your software, to your data analysis method, that observations from the same group are correlated and observations from different groups are uncorrelated. That's the kind of information in these matrices. Now, we have correlated observations, that's clear in our model. We assume that the responses are correlated according to these V matrices, and as soon as you have correlation, you need to use generalized least squares. On slide number 25, you can see the generalized least squares estimator for the factor effects you're interested in. And you can see that the estimator takes into account the V matrix, so it takes into account the correlation structure. The variance-covariance matrix of the generalized least squares estimator is shown in the middle of the slide, and the inverse of the variance-covariance matrix, called the information matrix, is shown next. And I denote that information matrix by M here on this slide. Now the variance-covariance matrix and the information matrix, they are very important matrices in experimental design because they summarize how much information you have about all your factor effects and what the precision is about all your of all your individual factor effects estimates. One important note about this slide, about all the formulas on this slide, is that the V matrix is unknown, so it needs to be estimated. And what Bradley Jones and I usually do is we use restricted maximum likelihood to estimate the V matrix. We use restricted maximum likelihood to estimate the variances of all the random effects in the split plot and split plot models. We use that technique because it works for balanced and for unbalanced designs. It works for models with interaction effects, with quadratic effects. So it's a very flexible estimation technique for variance components. Now, estimating the model is one thing. Setting up the experiment so that you get good estimates for your model is another thing. So now we enter basically the optimal experimental design phase. And to select a good experimental design, to find an optimal experimental design, we need some criterion. And back in 2007, Bradley Jones and I used the most commonly used criterion, the D optimality criterion, for selecting our split plot designs. And we did the same thing in 2009 to select our split plot designs. Now, a D-optimal design is a design that maximizes the determinant of the information matrix, so it is a design that somehow maximizes the information content about the unknown parameters, about the factor effects in the model. And you can also say that a D-optimal design minimizes the generalized variance about the model parameters. And because the optimality criterion sort of focuses on the variance of the parameter estimates, you can say that it is an estimation-oriented design selection criterion. In follow-up work, many years later, Brad and I also tried a few other things, and one of the things we did was we also considered the I-optimality criterion to select split plot and split plot designs. The I-optimality criterion has a different focus. That criterion does not focus on the estimation of the model, but it focuses on making predictions with the model. And more specifically, an I-optimal experimental design is a design that minimizes the average variance of prediction over all combinations of factor levels. And if you want to read more about I-optimal split plot designs, then I can refer you to an article that Bradley Jones and I wrote in Journal of Quality Technology in 2012. Now, regarding D and I-optimal designs, there's one technical note I have to make, and that is that D as well as I-optimal designs depend on the V matrix. More specifically, D and I-optimal designs depend on the relative magnitude of the variance components, of the variances of the random effects. Now, what we found in our research was that it's generally a good idea to assume that all the variance components in your model have the same size. And this gives you designs that work well basically for most practical scenarios. And that's also the assumption that I make in the next couple of slides when I create optimal experimental designs. So I assume that all the variance components are equally big. So that's the model and the design selection criterion. The next thing I want to discuss with you is that candidate set free algorithm, the algorithm that was named in the title of our 2007 paper. That algorithm is also known under another name. It's also known as the coordinate exchange algorithm. And the first authors to present a coordinate exchange algorithm were Meyer and Nachtsheim in a technometrics paper back in the 90s of the previous century. Now I want to illustrate the working of the coordinate exchange algorithm by looking at a very simple example of a split plot design, an example with one whole plot factor, one subplot factor, and one subplot factor. And the focus is on the main effects model. The budget allows for 8 tests, and we can only set the very hard to change factor, the whole plot factor, twice, and we can only set the hard to change factor 4 times. So what I'm going to do is I'm going to create a split plot design with 2 whole plots, 4 subplots, and 8 individual runs. On slide number 28, you can see a schematic representation of the V matrix for that design, the variance covariance matrix for that design. And in that picture, in that scheme, dark blue indicates strong correlation, light blue indicates moderate correlation, and white means no correlation whatsoever. The dark blue and the light blue rectangles here represent 2 by 2 matrices, and the dark blue rectangles basically mean that we have pairs of two very strongly correlated observations which appear in the same subplot, and the light blue rectangles refer to observations that are only moderately correlated because they appear in the same whole plot but not in the same subplot. Now, we took into account that variance-covariance matrix when creating a d-optimal split-split plot design for the simple setting that I just described. On slide number 30, you can see the way in which the coordinate exchange algorithm starts. The algorithm starts by generating a random design that obeys the split-split plot structure. You can see for x1, that's the very hard to change factor, that I only have two levels here, 0.25 and 0.57. That's random levels for the two independent settings of the very hard to change factor. For x2, I have four random settings for the four independent settings of that factor. And for x3, the easy to change factor, the subplot factor, I have 8 random values. And what the coordinate exchange algorithm does is it walks through the design, coordinate by coordinate, and it tries to optimize every value in that design matrix. And by optimizing every value, I mean the algorithm searches for the value that maximizes the determinant of the information matrix. And I will now click through the design. I will click through the next couple of slides, and you will see that the algorithm first optimizes the first row of the design. Next, it optimizes the second row, the third row, the fourth row, and so on and so on. If I keep on clicking, you can see that row by row, coordinate by coordinate, the design is optimized. And all the time, the coordinate exchange algorithm makes sure that the split plot structure of the design is respected. And eventually, we get the design on slide 38, where the determinant of which is nearly 28. And that design turns out to be the d-optimal design for the main effects model in one very hard to change factor, one hard to change factor, and one easy to change factor. So that gives you a very, very quick idea of how the coordinate exchange algorithm works. Here in this case, for this simple problem, the algorithm does a very good job. It finds the optimal design immediately. For more complex problems, you may have to run the coordinate exchange algorithm multiple times, because after all, the algorithm has to solve a very complex optimization problem, and that's hard. Then I reach the next slide, entitled Proof of Concept Example. This is one of the examples that appears in the 2007 paper. The design you can see on that slide is a d-optimal split plot design for a main effects model in 7 factors. And 2 of the 7 factors are hard to change or whole plot factors. I named them W1 and W2 in the table. And the 5 remaining factors are easy to change factors or subplot factors, and I named them S1 up to S5. Now, what I asked here was, I asked the coordinate exchange algorithm to create a design with 8 groups of 3, 8 whole plots of size 3. And a size of 3 for a group, for a block or a whole plot, in experimental design, that's sort of awkward, because it's very hard, it's even impossible to create a 2-level design that has the levels -1 and +1 orthogonal to the groups if you have sizes of 3 for the groups. So this is like a nightmare scenario for a classical experimental design person. In this scenario, it's just impossible to create an orthogonal design. And when you create a optimal design for that scenario, what is nice is that you can find the design with a very nice diagonal information matrix. You can see that very nice diagonal information matrix on slide number 40. So even though here it's impossible to create an orthogonal design, we can find a design that gives us independent estimates for all the main effects considered, and that's a nice feature. So that shows the power of that flexible optimal experimental design technique and the coordinate exchange algorithm. On slide 41 then, you can see the result of applying the coordinate exchange algorithm to the polypropylene example I discussed before. So here you can see the 20 best polypropylene formulations for the polypropylene experiment. And on the next slide, that is slide 42 then, you can see some of the best possible gas plasma treatments for the polypropylene experiment. And what you can see here is that every whole plot is used 5 times. So every box of polypropylene plates is used 5 times in the design that I present here. That's a constraint we imposed in the coordinate exchange algorithm. We explicitly asked it to generate a design with 20 groups of size 5, 20 whole plots of size 5. And that design turned out to be substantially better than the ad hoc design that I created at the time. So it results in substantially better estimates for these 66 parameters. So what I presented here today was the coordinate exchange algorithm, published in that 2007 paper, but there exist many other algorithmic approaches. I give a quick overview here on slide number 43. The nice feature of the candidate set free or coordinate exchange algorithm is that its computing time does not increase spectacularly with the number of factors. That's a big advantage compared to more traditional algorithms in optimal experimental design. More traditional algorithms are typically point exchange algorithms which require a candidate set, and that candidate set goes, the size of the candidate set goes up quite a bit when you study complex problems. Now, other algorithms take a somewhat different approach than the candidate set free and the point exchange algorithms that I published. In my algorithms, we did a simultaneous optimization of the entire design of the whole plot, subplot, and subplot parts of the design. In the approach of Trinke and Gilmore, is a sequential approach where first the whole plot part of the design is optimized, followed by the subplot part of the design, and for split plot designs, the subplot part of the design. Now, the most recent version of the sequential approach is very powerful in the sense that it is even capable to beat the candidate set free algorithm that Bradley Jones and I published back in 2007. In their recent technometrics paper, Trinke and Gilmore present a design for the polypropylene study that is a bit better than the design that Bradley Jones and I published. So you can see there are various algorithms out there to set up tailor-made experimental plans. Then I reach the discussion part of the presentation, and first of all, on the next slide here, I just give a summary of what I just said in the past 40 minutes. Using the principles of optimal experimental design, it's possible to conduct complex split plot and split plot experiments, And this is very useful whenever you have hard-to-change factors and whenever your experiment spans multiple steps in a production process, as in the polypropylene experiment, as in the cheese-making experiment. I've also talked about various kinds of algorithms. I think what algorithm you use is of secondary importance only. I think the most important thing is that you use a flexible approach to setting up your experiments, and that you should not be afraid to leave the well-paved path of orthogonal two-level designs if necessary. I think we have many algorithms out there now which allow us to be flexible in the experiments that we set up, and we should exploit that. Now, the Bradley-Jones Goos paper was published back in 2007, and we are now 9 years later. So a lot of things have happened in the meantime. I mentioned some of the follow-up work already in the beginning of the talk. I mentioned the algorithmic work by Trinke and Gilmore already, but there is more. And on slide 46, I mention a few things that have happened recently. First of all, one weakness of the work that we did in the past is that the optimal designs depend on the V matrix, depend on the variance components, and what we did is we just assumed that all the variance components are equal. That works well in practice. I'm still convinced that that works well in practice, but given that the computational power has gone up quite a bit since 2007, I think the neater way to handle this would be to use a Bayesian approach. And indeed, in recent articles, that Bayesian approach has been used in split plot and split plot contexts. Another thing that has happened is there has been a publication about a composite criterion that does not just focus on estimation of the factor effects, but which also takes into account the fact that you need to estimate the variance components. So your design should also provide information about the sigma squares, not just about betas. Well, there has been a publication about this. I will show you the reference in a minute. There has also been a lack of fit test. There has been a proposal for a lack of fit test for split plot and split plot data. That's sort of new. Lack of fit tests are emphasized a lot for completely randomized designs, but it was not yet clear how to do that properly for split plot and split plot data. Well, there is now also a proposal for such a test. And then finally, I talked about two different criteria, D and I optimality criteria. And in my work, I've always either generated D optimal designs or I optimal designs. Well, there have been recent publications where there was a simultaneous search for designs that perform well with respect to multiple criteria, for example, with respect to both the D and the I optimality criterion. And on the next slide, slide 47, I show you some references that contain some of these recent developments. That brings me to the end of the talk. I can see that I talked for quite a long time. I thank you for your patience and your attention.
Okay, Peter, thank you very much for the presentation and the enlightening overview of split plot and split plot designs. We now have discussion, and I'd like to remind people that everybody has the chance to contribute to the discussion. But first of all, we have a prepared discussant, Maria Lanzarat, who is an industrial statistician who works at W.L. Gore near Munich in Germany. She's also part of a global team of statisticians at Gore who work in design experiments, statistical process control, data analysis, training, and so on. And she has been at W.L. Gore since 1997, having previously worked in the pharmaceutical industry as a data manager in SAS program. So Maria is going to start off with some questions and discussion, and then we'll open it to everybody else. Maria, please.
Yeah. Hello, everybody. Thank you for your talk, Peter. I enjoyed it very much. And I would like to start with a pretty specific question on slide number 42, where you presented the design for the polypropylene experiment.
Slide
42.
Here it is.
That one. Yes. Where we can see the levels for the subplot factors. And you have the -1 and +1 settings, and sometimes settings around the centers. And for practitioners that I consult with, the values like the 0.2 and 0.1 are perceived as mistakes, and I have a hard time to explain that. It creates some mistrust in the design, although from a statistical point of view, I can see that is fine. And more important, for them, it is often hard to adjust these numbers precisely. So my questions on that point are, do you have a good explanation that an engineer can comprehend why you have these values? And number two, how adjustable are they? So do I do any harm if I change the 0.1 to a 0?
Yeah. Thank you for that question. So indeed, we can see on that slide that we have the levels 0.1, 0.2, 0.3, -0.1, and so on. I must admit myself, I usually don't like to see these values for the very same reasons that you named. So what do I do whenever I encounter these kinds of values in my ultimate experimental plan? Well, I always try to see what happens if I round the values.
Yeah.
And nowadays with modern software, it's really easy to evaluate slight modifications of your original design. And if I notice that there is no dramatic decrease of quality of the design, I just round the values.
Okay. Yeah, because
I must say, when you have really small experiments, then it may happen that these funny values, which we don't like, are actually substantially better than the more intuitive middle level, for example. The only way to figure out how bad rounding is by testing and checking. But I generally try rounding, and when the consequences are not dramatic, I present the rounded design to the engineer.
Sure. Another important aspect that I often see in practical applications of split dot designs, which I use in more than half of the experiments that I set up, is how can I incorporate a covariate? For example, sometimes we have a raw material that we use in a split dot design, and the thickness changes of like a little disk of material that we use. And you can measure the thickness of the material, but it's given in a way. We have to live with a range of thicknesses, so that is a classical covariate. Do you have any ideas on how to incorporate them into split dot design?
Well, in any case, a specific feature of the problem that you describe is that so you have given levels for certain covariates. So for these specific characteristics of your experimental design, you cannot really use the coordinate exchange algorithm.
Mm-hmm.
So for that part of your experimental plan, you have to switch back to the more traditional point exchange algorithm. So that's one technical aspect. I know that there has been some work on incorporating covariates when you plan your experiments. I also know that in the JUMP software that there are specific capabilities to handle covariates in the context of completely randomized experiments.
Yes.
I also know that in its most recent version, there's some capabilities to handle covariates for blocks. And then you have an experiment that looks very much like a split plot design in the end.
Yeah.
But the problem of having covariates and on top of that a split plot scenario, I don't know of any easy way to handle that.
Okay.
I'm sure it's not super hard to program it. I just think nobody has done it, and it certainly has not been implemented in user-friendly software.
Yeah. Yeah. In that specific case, I can determine the thickness before I run the experiment, so I can still group and treat it as a categorical factor, and say I have some light and thin ones and some thick ones, and then I think I can use this algorithm again. But
yes.
Yeah.
Yeah, but maybe that's not fully ideal yet.
Yes. Yeah, I agree.
So we have a couple of questions online, which I think the best thing is if I read them out. So the first one is from Tim Davis, who's asking, Peter, in your first 32 run example, factor W is changed 6 times and factor S is changed 5 times. So could you say something about optimizing the run order to minimize the number of changes of the hard-to-change factors, and whether your designs can be constructed to be robust, for example, orthogonal to run order or time trends?
Yeah, I will move back to the slide about the first 32 run examples. So I move back to the very beginning of the presentation to answer that question. I'm nearly there. So here we have that split plot experimental design. And what Tim observed was that the factor W, the very hard to change factor, is changed 6 times. For example, between whole plot 6 and 7, the factor W is not changed at all. And then between the other whole plots, I can see that W is changed very often. But in any case, one thing that I want to say about the split plot design here is that when you create a split plot design, you want the different groups, you want the whole plots to generate responses that are independent from each other. So you must make sure to have a proper split plot design, there must be a structural break somehow between the whole plots. So you have to start from scratch all over again for every new whole plot. Otherwise, you don't have a proper split plot design. And the question Tim asks is, can you optimize the run order so that you don't change W very often? You can do that, yes, but to have a proper design, proper split plot design with 8 whole plots, you would have to reset W 8 times independently. You need to reset W for every individual whole plot. And the same goes for S, the same goes for the second hard to change factor in this example. You must make sure that it's reset independently for every whole plot. Otherwise, you don't have a split plot design. But continuing on that theme, there have been proposals for alternative designs that leave the split plot data structure and that have a more complicated variance covariance matrix. And the designs that I'm thinking of are called staggered level designs. There have been 2 papers about that topic by a PhD student of mine and myself, Heidi Arnold. One of these papers has been published in Technometrics and the other paper in the Journal of Quality Technology, and that these staggered level designs try to reduce the cost, try to reduce the effort for resetting the hard-to-change factors even more than in a split plot design. So what you are looking at here maybe is, for example, a staggered level design.
Peter, the reason for my question was that when I used to run these sorts of experiments, my engineers were always very critical if I had more changes to these hard-to-change factors than strictly necessary. So if they're not split plot experiments, I guess, what sort of experiments are they? Because we could run that 32-run experiment with only making 1 or 2 changes to W and S. And that seems to me that in some sense that experimental plan would be more optimal than the one you're showing.
Yeah. So the design that you described with the minimum number of level changes for W and S, that would still be a split plot design if you have the structural breaks between your groups of observations that I described. The thing would be that if you go for the minimum number of resettings of the hard-to-change factors, then you cannot do a proper data analysis anymore. You cannot estimate the variance components in the split plot model or the split plot model, and then you can't perform tests anymore for the main effects and the main effects of W and S and their interaction effect. You can still do a nice data analysis for the easy-to-change factors and for interactions between hard-to-change factors on the one hand and easy-to-change factors on the other hand. You can still do that, but everything that only involves hard-to-change factors becomes troublesome because you cannot properly estimate the variance components. So in a way, cost-wise, what you described is indeed optimal, but analysis-wise, it's not optimal anymore because you sacrifice a proper data analysis for the hard-to-change factors.
I think that would be a sacrifice I would be prepared to make if it was a question of running the experiment or not.
Definitely. I fully agree with that. Plus, you cannot learn anything about the hard-to-change factors' main effects, but you can still learn about their interactions with easy-to-change factors, and that can be very valuable as well.
I think the other point that I always found useful for those of us working in engineering was that we can run confirmation runs quite quickly. So unlike agricultural experiments, you don't have to wait a year for the Earth to go around the sun, for example. So if you come up with an inference that says this combination is optimal, you can very quickly confirm it. I've always felt that that's an advantage we have in engineering over, say, agriculture and medical stuff.
Yeah, thank you for making that point.
Okay, perhaps I can ask Ben Parker's question now. So Ben, following on, is that Ben there? No, I'm not sure, sorry. Ben is following on from Maria's first question. So that was a question about the numbers, the 0.2s and -0.1s and so on. Ben is asking, is there any merit in having some kind of combined orthogonality and de-optimality criterion? So this might allow some properties of de-optimality without having these funny values, and moreover give good designs which practitioners might be more trusting of. And he says he's come across practitioners who are reluctant to accept alphabetic optimality.
Yeah. One thing you could do is, so I'm back at the slide 42 with the design that has funny values for its factor levels. What you could do is you could restrict your candidate set 3 algorithm to consider only 3 levels per factor. You could restrict the algorithm to just use -1, 0, and +1, and that would already be much better in terms of the aesthetics of the design. You could also try to enforce some more orthogonality in the algorithm. Yes, but my experience is to achieve perfect orthogonality, you often have to sacrifice estimability of interaction effects. So I would generally be willing to accept a tiny little bit of non-orthogonality in exchange for estimability of a large number of effects.
And there's one more question. Well, it's actually a comment from Tim just saying that including 3-level categorical factors in classical designs was discussed in the book by Grove and Davis in 1992. But he says no response required. And so that's just a comment. I would like to thank everybody for dialing in. We hope you found the session useful, and the podcast will be available on the RSS webinar website at some time in the future. So I would just like to wrap up by thanking Peter, especially, thanking Maria, and thanking everybody for joining, and have a good evening.